My name is Krishna KV. I am a PhD student in the EC department of IIC, advised by Professor Anurag Kumar and Professor Rajesh Sundaresan. Our work is on sequential detection techniques for monitoring the degradation of machines. Our emphasis is on rotating machines found in virtually all factories and industries. The health parameters of such machines are monitored by sensors which measure the vibration, temperature, and acoustic signals from the machine. The signals can be used to detect onset of failure in the machines. More specifically, we focus on monitoring degradation of rolling bearings, since bearing faults are the most common reason for machine failure. We concentrate our interest on mechanical vibration signals from these bearings. The power spectral density of these signals undergo a change after degradation of the bearing sets in. Here, we plot the power spectral density of bearings before and after the onset of defects. Notice how the frequencies appear in the PSD after degradation has set in. Thus, after degradation sets in, certain frequencies have higher energy in the power spectral density of the vibration signals. We select these frequencies for analysis. The frequencies which are sounded when the bearing develops a defect are well documented. These frequencies are called the characteristic defect frequency of the bearing and depend upon where the defect has occurred, whether the defect is an inner race, outer race, the ball, or the cage. We model these power spectral densities signals as having a certain distribution. That is, we perform statistical modeling of these signals. We model the signals as having a probability distribution before the degradation and having a different probability distribution after degradation has set in. We perform change point detection. That is, we look for a random time called a change point when the distribution of the signals changes from some distribution F0 to some other distribution F1. In our study, we focus on parametric distributions. These are a family of distributions where each member of the family can be specified by a value of the parameter theta from some set capital theta. We focus on the case of detecting change point when the distribution of data changes from some distribution f theta naught specified by a parameter theta naught to some other distribution f theta 1 specified by parameter theta 1. We study sequential detection techniques. These tests perform online detection, that is, a detection decision is made as and when a new sample is available at the detector. Quickest change point detection intends to minimize the delay in detecting the change point once a change has occurred by minimizing the expected value of delay to detection. This minimization is performed under a constraint on the false alarm performance of the detection procedure. The false alarm is measured by a parameter ARL to false alarm. This is the average time at which the detector declares a change even when a change is actually not occurred. We want to keep this average run length to false alarm ARL to FA as large as possible to minimize false alarms. Since we focus on parametric distributions, we study parametric change point tests, which test for a change in the parameter, that is, from some parameter theta naught to some other parameter theta 1. In real world though, such as ours, the parameter theta naught and theta 1 may not be perfectly known. Then the change point detection is called composite change point detection because composite hypotheses are involved. In our case, the parameter prior to change, that is theta naught, is assumed to be known. In practice, this parameter can be estimated very well from the machine data when it is known that the machine is running perfectly. The post-change parameter theta 1, though, is unknown, and it is known, and we assume that it is from some set theta, capital theta 1. Under this model, it is known that the optimal detector is a generalized likelihood ratio based QSUM procedure, GLR QSUM, which is shown here. Note that this here is equivalent to performing a maximum likelihood estimation of the post-change parameter theta 1 and then using this parameter to run a QSUM algorithm. This scheme has the following performance. The average delay to detection ADD is of the order h by the KL distance between the distribution specified by the post-change parameter theta and the distribution specified by the pre-change parameter theta naught. The post-change parameter theta, remember, is the true post-change parameter which is not known to the algorithm. The average run length to false alarm in this case is of the order e power h by square root 2h. Note that this h here that I am talking about is the threshold that we use for the scheme. This ARL to false alarm that this scheme achieves is actually less than the ARL to false alarm e power h that could have been achieved if the true post change parameter were known. So this difference in ARL to false alarm is the penalty that this algorithm has for not knowing the post change parameter. Now it is known that this GLRQ sum is extremely hard to implement. In fact, it cannot be implemented recursively in general and is computationally very hard. To overcome this problem, we propose our version of the detection algorithm. So our solution to this problem is that we propose a sequential detection procedure which is based on the GLRQ sum. Our algorithm has the advantage that it has a low complexity of implementation. In fact, our algorithm can be recursively implemented. Our algorithm achieves an false alarm performance, that is an ARL to FA of the order e power h. Recall that the GLRQ sum does worse than this. The average relative detection of our algorithm though is of the order h by I theta theta naught minus delta. Recall that the average relative detection performance of the GLR was just h by I theta theta naught. Thus our algorithm has a penalty delta, and this penalty is the cost that we have to bear to achieve this ARL to false alarm performance. In our algorithm, this delta is actually a user configurable parameter, and thus we can choose how much penalty we want. And that would change the average relative detection. Further, we are able to easily extend our algorithm to the case where multiple streams of data are available for detection of the change point. The challenge in this kind of situation is to efficiently combine decisions from all the data streams. This is called multi-stream change point detection, and we have shown that our algorithm can be easily extended to this case. The specific contribution of our work are that we have computed upper and lower bounds on the ARL to false alarm of our scheme. We've also computed bounds on the average relative detection performance of our scheme. In fact, we provide explicit computation of these bounds when the pre-change and post-change parameters are distributions are the exponential distribution. Finally, we carry out a simulation study of our algorithm. The performance of our algorithm was tested using synthetic data that modeled vibration signals from bearings. Extensive tests were performed in this study to check the efficiency of algorithm. We also ran our algorithm on real-world bearing datasets that were freely available, and we saw that algorithm did very well and detected the defects. We also compared our algorithm with existing algorithms in the literature for bearing defect detection, and we saw that our algorithm was better than them. Thank you.